Okay, and then in this slide, now we are going to study something called the diffraction grating. Okay, what is diffraction grating? Well, diffraction grating is in fact just many slits. So far we have learned the single slit case where n is equal to 1 and double slit case where n is equal to 2. Now the diffraction grating is simply the case when n is much larger than 2. Okay, and it looks like this. Here every white line corresponds to a slit, and there are many of them, right? Okay, so this diffraction grating is very useful in optics, and we will see why. Okay, and then we still consider them that each slit is separated by distance d, just like here. And what we want to know here is their constructive interference condition and also the destructive interference condition. The constructive interference condition is simple. The condition is just like in the double slit case. Why? Now let's consider only the two slits here. In the double slit case, we learned that the constructive interference condition is the case when the path difference between these two light rays corresponds to the lambda, which is a wavelength. And if this is different by lambda, this is another lambda, another lambda, another lambda, because all of them are at the same distance, right? So therefore, if one pair of light rays or one pair of slits satisfy the constructive interference condition, then all others will simultaneously satisfy the same condition. So therefore, the result just looks like the case of a double slit. So this is simple. Okay. And then how about the destructive interference condition? In fact, destructive interference condition is, we are not going to calculate it, but let me just explain it. You know, each wave is just like sine wave, and sine waves are moving from minus to plus, -1 and +1, right? Okay. So only when they exactly match, we are adding 1 plus 1 plus 1 up to n times. But if you are slightly moving away from this constructive interference condition, because now we have many slits, you are adding many sine waves which are slightly shifted away from each other. So therefore, at certain position, some sine wave will be positive, some sine waves will be negatives. So as a combination, if you sum them up, they just become 0. So therefore, finally, except the condition of exact constructive interference, everywhere else will just become 0. Okay, except the small range around the constructive interference. Okay, and given that, what we want to find is that what will be the width of this area where the bright bands appear. Okay, now in order to do that, let's compare this case with the single slit diffraction. You know, in single slit diffraction, we divided this wide slit into many zones, right? It just looks like this. If you consider this grating, whole grating as a single slit, and try to divide it into n zones, then it looks the same, right? So therefore, the intensity profile of the one bright band coming from this grating just looks like the central peak of the single slit diffraction, which is given like this. Okay, so let's try to figure out how wide this peak look like. And in order to do that, what we want to do is that now, in the case of single slit, we divide it into n zones of equal with delta y, right? But in this case, now we have to replace delta y with d and still use the same equation that we obtained from the single slit. Okay, and then now what we want to know is that what is the width of this peak. So therefore, let's try to figure out the distance between the center and then the edge of this peak. Now, this distance in single slit case corresponds to the position of the force minimum, right? Okay, so therefore, the force minimum in the single slit case corresponds to the edge of the diffraction grating's intensity. Alright, so using that idea, the position for the single slit was found like this: A sine theta equals lambda. So therefore, now we want to replace A with ND. So N number of slits is equal to the one single slit. So therefore you replace A with ND, and then that condition is the position for the half width. By half width we mean the distance between the center and the one edge, which means that full width is from one edge to the other, right? So half width is half of full width. So therefore this corresponds to the position of the first minimum, and then you can use the same equation, right? And then typically, of course, if you are far away from the screen, this angle is very small, and we learned that when angle is very small, now sine theta is just like theta when theta is very close to 0, right? Okay, given that condition, here we can simply drop sine. So therefore you can say ND theta half width is equal to lambda. So therefore if you rewrite it, now you find that half width of theta is equal to lambda divided by ND. So what does it mean? We have to get an important lesson from here, so that half width of this is inversely proportional to the number of slits. Okay, so if you make a grating with many slits, then the peak will get sharper and sharper. So because this peak will get sharper, it is easy to figure out where precisely the constructive interference happens. So because of that reason, now this becomes the useful device, much useful compared to the double slit. Okay. Okay, so far we have studied the diffraction and interference, and in this final slide of this chapter, let me tell you how useful this diffraction method is in trying to figure out the nature. Okay, so on the right side we have a figure for the atomic structure or crystal structure of sodium chloride, which is just a table salt. Okay. Chemically, this sodium chloride is made of sodium ion and chlorine ion. So for example, here the blue dot represents the sodium ion and red dot represents chlorine ion. And as you can see, they are positioned periodically exactly at the same distance. And now we know the exact value of the distance between them. And how do we know? Actually, the reason why we know this is because we can have the X-ray diffraction experiment. Okay, and why X-ray? You know, if you look into this material, the distance between atoms, actually distance between atoms in any material is more or less in the range of angstroms. And what is angstrom? 1 angstrom is equal to the 10 to the powers of minus 10 meter, which is a very small distance. But this distance is comparable to the wavelengths of X-rays. Compared to that, the visible light has a wavelength somewhere around 3,000 to 7,000 angstrom. So therefore, the visible light has a very long wavelength. So therefore, you cannot observe these atoms using your eyes. You need to use the X-rays, and X-ray will produce diffraction pattern. Okay, how does it do that? When you shine X-ray into these atoms, you know, X-ray is an electromagnetic wave which has an electric field, and electrons in atoms, of course, are charged particles. So therefore, electrons will interact with X-ray and produce spherical wavelets due to the Huygens principle. Okay, so each atom will produce a spherical wavefront according to Huygens principle, but what we eventually observe is a combination of their wavefront, right? Okay, so to make things simple, we can just think about it as a plane wave coming in and coming out, and how it comes out. Now we can imagine there is a mirror inside the crystal. What kind of mirror? The mirror made of atoms. Okay, for example, here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and more of atoms. You can imagine there is a plane like this, And when atoms on this plane are producing scattered X-rays, it will just work like a mirror. So when things come in, they go out at the same angle, just like figure here. Okay, and as you can see, because atoms are periodically positioned, if you can imagine there is one plane like this, then there is another plane over here, and then another plane here. So all of them work like a mirror. So then when the light comes in and reflects from here, some part of the light will go through into the second layer, and there will be the reflection, and then there will be the path difference. So following exactly the same procedure we have learned so far, there will be a diffraction and interference. Okay, so our task here is trying to find what will be the condition for the constructive interference. Okay, now let's assume that the distance between these two mirrors, imaginary atomic mirrors, is d. Okay, and then now these light waves, X-ray light waves, have to go into the mirror and then come out. So therefore, if you look at this figure, now the path difference between this ray, which is reflected from the top layer, and this ray, which is reflected from the bottom layer, is this much. This much is the path difference. And then here, the situation is similar to the case of double slit or the grating, but only difference is that this X-ray has to go in and come out. So there is a twice the length difference. So therefore, the path difference becomes 2d sine theta. And according to what we have learned so far, if this matches the integer multiple of the wavelengths, that will be the constructive interference condition. So therefore, finally, we can find the condition that 2d sine theta equals m lambda, m for all integers, is the condition for the intensity maxima. And at the same time, in any real material, how many layers do you think there are? There will be almost nearly infinite number of layers, many layers. So it is just like diffraction grating instead of double slit. So therefore, each peak will be very sharp like this. So therefore, the pattern will somehow look like diffraction grating. So therefore, what you need to find out is only the constructive interference, and this is called the Bragg's law. Okay, so these phases, okay, these two persons, William Henry Bragg and William Lawrence Bragg, is father and son team who discovered this method and got the Nobel Prize. So therefore, when you actually do this experiment, you not only have to do it once, but you can actually perform similar measurement along different orientations. For example, here, first you find the mirror like this, but at the same time, you can also find a mirror like this, and maybe also a mirror like this. So there are many mirror planes you can think of. So you can repeat this measurement many times and eventually figure out the distance between atoms. That's how we know the distance between atoms in real materials. Okay, so here let's try to remember this Bragg's law. And then Bragg's law looks similar to the case of diffraction grating, but we have a factor 2 because the X-ray has to go in and come out. Okay. Alright, finally let's make a summary of this lecture. Here we first learned the diffraction from single wide slit. Okay, as a summary, let's try to draw the graph of the intensity pattern. From the single wide slit, the pattern looked like this. Okay, so and this position, which is central position, and the first minima, second minima, all of them can be summarized into this single equation, which is a sine theta equals m lambda. Okay, and then we also learned the double wide slit case, which was the combination between the double narrow slit and single wide slit. So in this case, the pattern, actually the envelope of the pattern looked just like single wide slit, but in detail we had this small peaks going inside this envelope. So this width, with a distance between these peaks, could be written as d sine theta equals n lambda, which is just like double slit case. Okay. And we also learned the diffraction from grating. So the constructive interference conditions for the grating was same as the double slit case, but the width of each peak was inversely proportional to the number of gratings. So if you have many gratings, then peak will become sharper and sharper. And finally, we learned the diffraction from crystal, in which the Bragg's law is written with the factor 2d sine theta is equal to n lambda. Okay, so please compare all these and then try to remember. Okay, if you understand this all, it'll be great. Okay, this is the end of our interference and diffraction, and we will skip chapter 37. This is about relativity, which is a very difficult topic, so we will skip it. And in the next 2 lectures, in the next 2 weeks, we will study quantum physics, which is also a kind of new modern physics, and it is a completely different idea, but what we have learned about waves is still very useful. So it's basically about waves and particles at the same time. Okay, so I will see you on the Thursday's classroom lecture, and I will also meet you again on the online lecture next week. Okay, goodbye.